I'll welcome the second speaker of this session, Prof.Sumati Surya. She's a faculty at Theoretical Physics Department and she works on classical and quantum gravity with primary focus on causal set approach. And she's going to talk about understanding space-time using causality and discreteness.
Okay. So thanks all of you for being here today. I'm really happy to be talking to you. Just a small disclaimer, I've not been feeling very well. So if I run out the door in the middle, excuse me, I'll continue the talk later in the week. But anyway, I just hope the adrenaline will do the job and I can give you the enthusiastic talk that I meant to give. Okay, so today I'm going to tell you something about doing quantum gravity by quantizing the causal structure. Here's the outline of my talk. I'll begin with the question, why quantum gravity? I don't intend to be apologetic about quantum gravity in the slightest, but I want to kind of try to see if I can convince you that it is in fact an interesting question to ask. And then I'll say a few words about the space-time causal structure, which is what we want to quantize in this particular approach to quantum gravity called causal set theory, and discuss some of the basics of causal set theory, some research highlights in the last 19 years that I've been here, and finally a surprising connection to something actually practical, because all of you talk about a lot of practical things. So I decided to start my talk with a couple of cartoons. Apologies for the crude pictures, but why quantum gravity? All of you have talked about some really interesting physics based on, of course, some known physics, but also looking for new things in the world around us, supported by experiments and so on. And it's a very rich world, and often when I listen to it all, I think, oh, that's really interesting. Maybe I could have done that at some point, right? So it's all very interesting stuff. It's not for lack of interest, but some of us do kind of peer over the edge, okay? And apologies, Madhavan, I don't necessarily mean that all quantum gravity people do it, but sometimes I do feel I'm on the edge of what's known. And as I don't like to use this because it's by somebody I don't like, but it's really like the unknown unknowns, okay? So today, for the next 40 minutes, just for the next 40 minutes, I invite you to come peer over the edge with me. And I hope I can convey some of that excitement of why we do, why we look for things that are possibly, don't have very obvious experimental signatures. So why quantum gravity? Let's just look at the magic of constants. Let's start with Newtonian gravity, which is historically the oldest. We have a constant, a fundamental constant of nature, which is the gravitational constant. And then we have special relativity, which has the speed of light as its fundamental constant. And then we have quantum theory, which has the Planck constant. When you put together special relativity with Newtonian gravity, you get at least the constants that give you general relativity that govern the strength of the gravitational field in relative gravitational field, which is C and G. When you put together special relativity with quantum theory, you get the field of quantum field theory, which is one of the very, very rich areas of physics, you've heard about Higgs and so on. All of this results from this particular theory here, which is also called relativistic field theory. And so it's of course natural to say, okay, put them all together, what do you get? And of course there's a song like that, but I won't sing it, promise I won't sing it. And surprise of surprise, you get out a length scale and you get out a time scale. Okay, so it's very curious. But hey, let's look at those numbers. It looks really small. And yes, when you look at it, you say, oh, can't possibly be anything relevant to anything we know. It's not interesting. Okay, so let's try to compromise a little bit and say, let's take quantum field theory, which we know it's a very robust theory that has been tested brilliantly in the last century. And let's take general relativity, which also has been tested brilliantly, including the recent stuff on gravity waves. General relativity is made up of a piece. On the left-hand side, the equation is got to do with space-time metric and curvature, geometric properties. And on the right side is matter. It's a stress-energy tensor. So what you have is matter that responds to curvature, and curvature that responds to matter. It's a nonlinear equation, and so they're put together in this way. But quantum field theory, the stress-energy tensor just doesn't appear like a classical stress-energy tensor. It appears as an expectation value in some state, say the vacuum state, if you like. And so really, if we know about quantum field theory, we also know about classical general relativity, we try to put them together, then we have this odd kind of equation, which has a piece that is a classical piece and a piece that's a quantum piece. And really, that quantum piece, because quantum theory involves fluctuations, it's not something that is deterministic in quite the same way as classical mechanics is. And so that's going to have a feedback into the classical. So it feels like a very made-up kind of theory, something which can't possibly be consistent. So you can't really retain the notion of a classical space-time when you have a quantum matter, because everything gravitates, including the quantum matter. And so gravity has to, in some sense, you can't really remain classical in a fundamentally quantum world. Okay? So there's a reason why we think there's some theory that's beyond just the theory of a quantum field sitting on a classical background. There are also issues with general relativity. There are things called singularities. If you run space-time backward, our expanding universe backward in time, all the way to the very beginning, we come across something called a singularity, where the curvature of space-time is just too big. And we don't know what happens there. Every notion of space and time that we know breaks down. And this is a feature of general relativity. Even if you start off with local equations that look perfectly fine, the evolution leads you into singularities. Not very dissimilar to fluid mechanics, where you can have singularities developing and so on and so forth. But here we're talking about space-time, so there's some sense that something should replace what's happening at singularities. These are also hidden behind black holes, for example. And when you do this kind of a theory, when you have quantum fields sitting on classical backgrounds, you also have weird phenomena happening. Black holes, which are, have horizons. You can't see, into a black, cannot get any information out of a black hole. But when quantum fields interact, you have this weird thing that happens. There's pair production that happens at the horizon. So you throw in a quantum field, and the black hole begins to radiate. And even though it's supposed to be black, it still radiates, and it radiates out a gives out thermal radiation. And it leads to all kinds of interesting conundrums, including something called information loss, because the black hole is shrinking, but all the stuff that's coming out is thermal. So even if you throw in, as they say, an encyclopedia or some really coherent information, you lose the information in the form of thermal radiation. So there's all kinds of interesting things that come out of this. But today I'm not going to talk about the reasons, only the reasons why we study quantum gravity.
Quantum field, what do you exactly mean? I mean,
just quantum fields, which are the idealized calculation that is done is you have something coming from asymptotic infinity, a scalar field, for example, and impinging on the black hole.
Okay.
And then there's pair production that happens on the horizon, and so some stuff comes out, some
scattering.
Yeah, it's a scattering. It's basically doing quantum fields on a curved background, which has many surprises, and this happens to be one of them. So typically when we talk about the quantum field theory, the successes of quantum field theory are all, or most of them, I would say actually all, are in flat background, okay, without curvature. You really don't know that much about quantum fields on curved spacetime. So that is in itself an interesting, rich field. But okay, so how do we quantize gravity and what do we mean, right? What is the object we should quantize? So very naturally you'd imagine that the gravitational field, just like electromagnetic field, quantize it like you do the electromagnetic field. And that was the initial idea, that just as you can quantize the electromagnetic field and get a very successful theory of quantum electrodynamics, even though there are infinities there and so on, we know how to deal with them. It's a really well-behaved, excellently, the experimental evidence for it is brilliant, so on and so forth. It's a very, very good theory. So why not do the same with gravity? And that's what people tried to do, but they found that the theory has a property of, quote unquote, not being renormalizable, which means that the more, that you go higher and higher, you get new coupling constants constantly coming into your theory. So you can't control the theory in quite the same way. And typically for theories that are of this form, you imagine that there's some underlying theory. This is only an effective theory, okay? So you imagine that there's an underlying theory there. So there's something wrong with the way in which we treat quantum gravity, when we treat quantum gravity just like another field. And if you step back a minute, you'll kind of understand why that may not work. Because, and here's an analogy which I think can be traced back to Wheeler, but I heard it from Abhay Ashtikar, which has always stuck in my mind, which is that think of a stage where you have actors coming on the stage, and they perform their play and they leave. Okay, that's Minkowski spacetime. The stage is flat spacetime. Now, when the stage itself becomes dynamical and quantum at that, then you don't know which is the actor and which is the stage. So it's trying to figure out, when you have a background which itself gets involved in the quantum theory, this is a very, very hard problem, and this is why we are still doing quantum gravity today, still trying to understand, what exactly one should be quantizing. Okay, so it's a very hard problem. And so, oops, I should actually just use this. So one question you can ask is, if I'm not supposed to treat it like a field, what should I be quantizing? So there's many options that we have. First is just a metric, which you could use as a field, but then you could also think of quantizing the derivatives, okay? That's also the connection that you have that tells you how things change. And we have things like string theory. That's one way, a completely different way of quantizing gravity. Then you have triangulations where you can discretize spacetime using just simplicial, like the buckyball or something of that sort, right? You can just use it and discretize spacetime like that. And what I'm going to tell you about is discretizing using the so-called causal structure. For that, I'm going to have to do a little bit of rewind and remind you again of some aspects of special relativity. For those of you who know this very well, I apologize. But I think it's a good review of it. It's a useful review. So when I think of a space-time, I've got a metric here, GAB, which is a symmetric n cross n matrix, if you like. And this is the gravitational degree of freedom that we talk about in general relativity. In Riemannian geometry, metrics appear all the time. You have curved space-time, curved objects all the time. You know there's a metric there and you can talk about it, okay? What's different about space-time is that the geometry, the line element, so to speak, has this very important minus sign sitting here, okay? It's what's called an indefinite signature space-time, and because of that, distances come in different flavors. So distances can be either negative, positive, or actually zero, which means you can have two places which are very, very far apart in the Riemannian definition of being very far apart. But with respect to the Lorentzian geometry, they're very close. And so here's my cartoon of that. When you have these mirrors, these rear view mirrors, they often say objects may be closer than they appear. Events are in fact closer. Everything on your past light cone is at zero distance from you. Okay, so it's a completely different way of thinking about distance. And this is something that your first course in special relativity is talking about. It's talking about light cones. It's talking about actually relations. So if you look at an event here, it has a future light cone and it has a past light cone, and the boundary of that light cone are the null related points. Okay, so this is a very important structure. Hidden behind all of this is an ordering relation. And that is that in any event, okay, so this is an event, and this is another event. This follows this. This is causally before this, okay? There are two events. And that relation, that ordering relation is going to be what this talk is all about. So just this little slide, please be with me. What's important is that in a space-time where I can't go and kill my grandmother or my grandfather or great-grandmother, which is I don't allow closed time-like curves or time machines, this relation is not cyclic, okay? It is, so it has this property. It's also transitive, which means that if x precedes y and y precedes z, then x precedes z, which means that the light cones are nested one inside the other. So if this is to the past of this, it is also to the past of a third event here. Okay, that's all that transitivity is. From that space-time, I can extract then the set of all events, just the set of events, just think of a set of points, events, and this ordering relation. And that's called, because it satisfies these two conditions, it's a partially ordered set or a poset. And it's called the causal structure poset. And it's there in every space-time that we have, which satisfies causality. Okay? You notice that if I take the line element and I multiply it with a constant, actually it's a scalar, okay, in front of the line element, then the zeros continue to be 0, right? Distance at 0 continues to be 0. So under such a transformation, the light cones remain invariant. The light cones don't change. So which means that under such a transformation, this causal structure poset remains invariant. Okay, this is very important because light cones remain invariant even though you've changed the volume and everything of the space-time. Okay, you've made something double the size or triple the size, it doesn't matter, and you've done it in different places in a different way, but still the causal structure remains invariant. Okay? And the interesting thing is that this does not exist when you have two time directions. Suppose you said, oh, I want to go to a really exotic space-time which has now two time-like directions, two time directions, then because those time directions are connected, I can't have this disconnected future from the past. So I won't have causality in such space-times at all. I won't be able to say what's before and what's after in such a space-time. So this existence of this poset is almost like a fingerprint that we're in Lorentzian, so-called Lorentzian geometry. Okay, so it's very essential to the notion of a Lorentzian geometry. Okay, so we have, so let's look at this relation, and I think of one of those tablecloth tricks. Okay, you set everything down on a nice gridded tablecloth, and then you whisk it away, and you only have the stuff that's remaining, and now that you want to say which is related to what. Okay, so think of a lot of what I do now will be this kind of tablecloth trick. And the question is, should I quantize a metric or should I quantize this causal structure? And why would I do that? This idea actually goes back even to, even not quite the, I guess Riemann doesn't belong to this list quite, but he belongs to the list of people who wanted to discretize space. But Penrose, Cronheimer, and others who came up with this idea. And the idea that causal set theory comes up with is to say, okay, so I think I missed something here, which is, maybe it got left out, which is that I can think of space-time, okay? If I think about this in this way, then the only thing that's missing here is this overall scale factor. So if I have a metric, and it's a symmetric metric with so many degrees of freedom, then the only thing that's missing is one scalar degree of freedom. So the causal structure poset, this poset order theoretic object has everything about the space-time except for 1 degree of freedom. Okay, yeah.
So I have a very basic question. Like, see, like when you have like a usual without the time when you do this distance, so you have ds square equal to, let's say, dx square dy square dz, yeah, and distance is the square root of that usually, and which is always real. It can be, you can take either plus or minus. But here you define distance as a square, is it not the square root of this object?
Yeah. So I mean, it can be, so as you saw, because ds squared can be negative, so it's imaginary. So mathematicians never liked this way of thinking about it. But on the other hand, this is what space-time, how space-time behaves, and all your, all the solutions of Einstein equation have such metrics with minus plus plus signature. So that's how space-time behaves. Okay, so the point is to go back there and say, well, what is the thing that makes it, that you can extract and that you can quantize? And so you can think then of space-time as this causal structure poset plus 1 scalar. Sadik, pucho. Pucho. Kyun kar rahe ho ye? Anyway, 1 scalar degree of freedom, okay? So there's only 1 scale degree. You can think of it as something that blows up stuff, and so there's everything else is contained in the ordering relation. And that's basically what one is doing in causal set theory. We're saying, let's take that causal structure and let's discretize it. Yeah.
In the previous slide, you have equation for cosine as the next slide. The first equation, what is
Oh,
epsilon?
that is what, okay, I forgot that I had written it, okay.
Okay.
Yeah, this is the one that I want to say. You can think of causal, the space-time as causal structure plus this volume element, okay, which I've denoted by what's called the volume form, which is at every point. Yes, go ahead.
Is everything time reversible, is symmetric?
It depends on what, so let's look at Minkowski space-time, it is. Let's look at FRW, it's not.
What is FRW?
Sorry, Friedman-Robertson, the universe we live in, it's not. Run backwards and you run to the singularity.
But
It's not, I mean, you can run it backward and forward, yes.
you
But
can
it's
run it
not going to be symmetric, right? And there's a,
So the question actually is that, look, for instance, in the present paradigm of quantum physics, I mean, there is the unitary evolution and then there is the measurement which it gives you the collapse of the wave function. So how does this formalism take such things into account where you have to deal with collapse? Since you
very
have to
good question.
join-
And I will come to things like dynamics eventually. Right now we have to, I'm just really doing 101 of this, which is saying that what should be quantized, okay? So we know when we do quantum theory, even when we look at constrained quantum theories with constraints on them, that is not as straightforward as all that. You look at systems in which, you think, okay, you just do phase-space quantization and you can run away and you've got to, but quantization can be very complex in more complicated systems, and gravity is no exception. So we have multiple ways of quantizing. We don't know if they're going to be equivalent, but we have to try and check the multiple ways of quantizing. Yeah.
Hey, how do you incorporate this SI click condition? Is it just mathematically, how do you implement?
Sorry?
SI click, so is it there in the theory or you?
Right, so that's a very good question. Einstein's equations are local. They don't tell you anything about global structure, okay? And so you can, from Einstein's equation, there are solutions in which you can actually get, and the simplest one is really if you take a piece of paper and fold it around this way and call that time. That's also a solution of Einstein's equation. It's a flat solution, but time is going around like that. Now, I would say that we are employing the principle of causality. I didn't state it very explicitly, but the principle of causality to say that such spacetimes are unphysical because they would run into all kinds of conundrums, all kinds of problems, and we stick to broadly only those in which you have causality. So causality becomes a principle, which is why we impose the condition of acyclicity to any spacetime. Okay? So, and it's, yeah, so you can argue whether that's cutting out stuff, but in my opinion, that's a fairly good principle to start, very robust principle to start off with, because we have no evidence otherwise of acausal behavior.
Thanks.
So the hypothesis basically says, okay, we were missing that volume element. We don't know how the local volume element goes. That's one missing ingredient. But now let's do the following. Let's discretize, which means that the set of events, the set of events that's to the future of this and to the past of this. So both to the future of the first event and to the past of this, which means it has to be within that light cone, okay? These are what we call causal diamonds, okay? Within that space-time interval, the number of fundamental space-time events that are there, how would we think of the continuum? We think there's uncountable infinity of possible events. But now the hypothesis is saying there's actually a finite number, a very large number, because Planck's scale is so small, but it's still finite. Once you impose that condition of finiteness, you can do something very interesting. You can extract from, instead of space-time volume that was missing, you just count. You count the number of elements between, fundamental elements between two events, and that gives you the space-time volume in the units of discretization, okay? Which may or may not be the Planck scale. So that's how you discretize space, and you also get out the volume element. So the hypothesis is that you discretize space, so you, instead of a continuum, and this is where there's a lot of analogy with what people do in condensed matter physics. You don't think about the continuum. This table is, built of molecules and various other molecules, atoms, and so on. It's a fundamentally discrete object. It looks continuous, but it's fundamentally discrete. And so the continuum emerges in this picture. Space-time is not something that can be gone to arbitrarily small time scales or arbitrarily small distances. There is a fundamental space-time cutoff. Okay, that's the hypothesis. Okay, and that's where we begin, and that's where we start to work with. And so order, which is just the ordering between these events, so you have now a Poe set, but that partially ordered set is also locally finite, because I said that there's only finite number of atoms in any space-time, finite space-time volume, and it's only in an approximation that the continuum comes out. So at the fundamental level, space-time looks nothing like the continuum. That's the hypothesis. It's only when you look at it from far, at larger scales, that it pops out. Okay? So here's the full hypothesis. You say that the fine-grained structure of space-time, and that's the real object that we have to look at, are these locally finite partially ordered sets. Okay? They're just these graphs. So imagine all of space-time is just a graph, okay, with an ordering. And I want you to think about the following. When you're measuring something, I want you to see if you can really come up with a measurement which does not involve causality. Okay, if you can, I'd love to hear about it. But please, that's a really nice, fun experiment to try to do, because we're so used to thinking of spatial things, but everything we do is actually a causal process. You cannot do any measurement, really strictly speaking, spatially. Everything is a causal process. So, okay, that's the idea. And then we have, very importantly, because we want to replace space-time in a sensible way, we want there to be a number to volume correspondence. We also look at causal sets that are extracted from a continuum via a random process. So you have a random lattice. We don't have regular lattices. And this random lattice we generate through a Poisson process, okay? And here's just a quick reason why we don't use a regular lattice. This is a, light cone lattice, so two light cone coordinates like this in 2 dimensions. If I had a region of space-time here, which I said, it has so many elements in it, I want it to be invariant under all the symmetries of the space and any coordinate changes as well. So if I did a Lorentz boost, which acts in a very different way from, say, a rotation, right? I mean, Lorentz boosts, they basically have invariant hyperbole, then that region becomes completely empty and there's no way in which you can do a number to volume correspondence. So the only way we know how to do it is to do a random lattice, so that on average the number of elements or the number of events, space-time atoms, is proportional to the space-time volume. Okay? It's a statistical, and at this level it's a classical statistical ensemble.
What determines rho?
Rho is your discreteness scale. So it could be Planck scale, but you can leave it as a free parameter in your theory. So just quickly, there's a prediction. So even though this sounds very fanciful, this very simple picture gave rise to a very startling prediction from due to Raphael Sorkin in 1987, before there was any knowledge of that there was dark energy at all. And so the argument is very simple, so I'll just go through it quickly. In the Einstein-Hilbert action, if you look at how the cosmological constant term, which is basically the dark energy term, comes, lambda is a constant, and it comes in this way where dV is a space-time volume. Okay? So the metric is all included in there. If you think about it, this is a constant and so on, you can think of these two being canonically conjugate to each other. This is a very simple argument, but that simple argument gives you, it's a basically back of the envelope calculation, gives you the order of magnitude. So if they're canonically conjugate to each other, then you know that the fluctuations are related thus. But because we have a Poisson distribution, the volume, which corresponds to the number, fluctuates like square root n or square root v. And when you put that in, the fluctuations, and you use this in the fluctuations of lambda in this constant, but the quantum fluctuations of lambda go like this, and it gives you exactly the value of the cosmological constant, the order of magnitude that was not possible to get. I mean, the quantum field theory value is 240, 10 to the 240. It's just completely huge in comparison. And this is actually exactly of order of magnitude. So this, of course, requires a lot more, connection to observation and so on. And there's been a body of work that's happened after that. So I won't say anything about it. But this is actually a very, sorry?
Lambda is some kind of pressure, is it? Or?
No, it's the cosmological, it's a constant that appears. It's, so in this, in this fluid membrane, where did I
No,
go?
because you said it's conjugate to the volume, so that's why.
Sorry, I just seem to have jumped. Oh no, I'm going the wrong way. Yeah. Okay, yeah. So it's the fluid membrane analogy, which Sam and Suparna use in a very nice way, was to say that it's like the surface tension and area. That's the kind of, so the units are of course 1 upon L squared, length squared, and that's how it comes in here. So there's a very nice analogy which nicely written paper. So what I will do now in the remaining part of the talk, I don't know when I started, so 3 o'clock, okay. So since I've already taken up 40 minutes, I will lead you closer to the precipice. In the last 19 years, the kind of stuff that I've been doing, it involves a question, where is geometry and topology hidden in the causal set? Because I've said, throw away all the continuum, I've only got these ordering relations, and from that ordering relation, I want to be able to reconstruct space-time, okay? How do I build a quantum dynamics of space, of causal sets? And also something that we've been looking at more recently is how does discreteness change the ultraviolet behavior of quantum fields? Because quantum field theory is known to have these ultraviolet divergences, and here you have a natural cutoff. See, those, even if you do field theory and condensed matter physics, you have a cutoff. Okay? And here we have a cutoff from the space-time perspective. So how does that impact quantum field theory? And these are all the people I've worked with. I've had 2 PhD students, Noman and Abhishek, both of who've completed. Also did work with students on their PhD thesis. The first four who were not strictly my PhD students. I've had lots of VSP students. I've listed them all here, and of course many others. So, okay, so here's the first question. So I want to, like Sandrika was saying yesterday, building up things using Rydberg atoms, right? Building structure from atoms. Here I want to build up space-time from space-time atoms and the relations that they have with each other, okay? That's all I have. That's all I'm given. And from this, I have to get out space-time dimension, topology, geometry, everything, okay? So it looks like a rather daunting task, and it is, but here's one of the early results that came out, which is that if I have this set, so here's my bulk, here's my continuum, I've got a Poisson distributed set of events on this, and now I whisk it away, I do the tablecloth trick, I don't have the space-time anymore. I have only these events, and I have the relations between them. From that, what geometric information could I possibly get? So the simplest one is if I take, so these are chains, these are things that are related to each other, okay? And I haven't drawn all the relations in this, but if I look at chains of this kind, and I say what is the proper time between this point and that point, and I calculate the length or the number of intervening points that I have, events I have, of the longest one that I get, the longest chain that I get, then that's proportional to the proper time. And for any of you who remember special relativity, proper time is something that maximizes the time, okay? It maximizes, the part that maximizes time is the shortest, gives you the proper time, okay? So this is really important, and so this is where the length of the longest chain is the one that gives you, it's proportional to the proper time. So just from this very discrete substructure, if you know, you of course need to know the information about the density, the cutoff that you're using, accordingly you get a formula, okay? So this is something that was done very long ago. Here we've been interested in asking for questions about induced spatial topology and geometry from order. I realize now most of my talk is from now on, so I'll try to really rush, but I'm happy to come back to any of these slides at any time. And one of the challenges that one has in causal sets is because it has a very important feature of being non-local. So if I think of a lattice, a regular lattice, right? I think of a grid. If I look at a point on that lattice, it has a finite number of nearest neighbors, right? I mean, I just have 4, for example, on the plane, and so on. In this kind of lattice, in this random lattice, because of Lorentz symmetry, I have this very weird thing that happens, which is that every point has an arbitrarily large number of nearest neighbors. They go all the way up the light cone. So what's close to me, and that cartoon that I gave of the car rear view mirror is kind of like that. All of that is close. Everything is close. So if you want to just have the nearest neighbors in terms of these relations, then you really have, every point has an infinite number of past nearest neighbors and an infinite number of future nearest neighbors in Minkowski spacetime, for example. So it's very hard to do things with spatial hypersurfaces, which means that at any moment of time you give me initial data and I allow it to evolve. But there is a way of getting around it, and that is by constructing these elements which are not related to each other. Those are spatially related to each other. So in other words, there's no relation in the partially ordered set. They're unrelated, and you construct these, and from there we can do many things. So we call them anti-chains because they're not on a chain, they're anti-chains. And you can construct many things. You can construct topological invariants. You can also construct induced distance measures, and that's because one can actually take this spatially related points and extract information from the causal structure above and below, okay? So you can think about that as a way of extracting information about a spatial distance by, going backward and forward in time, causally. So this is a way of defining a distance, and this is something you can think about. How do you actually measure a distance? It's effectively something of that sort, okay? So this is a work we did on generating induced distances, so geometric information. We also have space-time dimension estimators. It's really too little time for me to say very much about this, but if anyone has questions, I can go over this in more detail. And just to say that all of it reduces to counting, okay? So what you do is you have this mass of points and you have relations. Now, how can I extract geometry from it? I look for relations of a particular kind. So I say that I'm going to look for the number of relations. Just count all the elements that are related to each other. How many of them are there? Okay? I can put it into this formula and get out the dimension of the space-time. Okay, and this can be simulated, this can be checked. So dimension can come out just by looking at how many objects are related to how many others, right? So how many pairs of related points do you have? Then you get out this very important, as whether you're in two-dimensional space-time or three-dimensional space-time, just based on the number of relations you have, okay? You can also count intervals, which is different sized intervals. So if I have an interval like this, which has 5 elements between it, right? 5 events that occur between it, I can count how many such events are there in that causal set. And when I do that, and I do it for all possible sized of intervals, just counting that will again give me a dimension estimator, okay? And this is something that we've done and generated and seen how good the fit is with the continuum dimension, okay? We can also do curvature estimators just based on counting. So we take chains, so a relation is a 2-element chain, okay? Just 2 elements are involved, but you can have one in which 3 elements are involved. X precedes Y precedes Z. So count all such relations, then count all 4-element ones. You keep doing that in that causal set, and you get out an estimator for the curvature. And this was something we did quite a while ago. And even when you count the intervals, then you can actually get the curvature, but also get a very important thing, which is the discrete Einstein-Hilbert action. And this allows us to go much further. And I'm just going to mention some work with Anish here, where because of the fact that we have, if you think about it, we have a Poisson distribution. So think of a random lattice, or just think of throwing a bunch of random points on this table. Suppose I had a particular surface I wanted. Okay, so I mark out a circle here. What is the probability that that circle will actually be realized? It's 0, right? Because it's a set of measure 0. Because this depends just on the area, the 2-dimensional area, not on the 1-dimensional area of the circle, so the length of the circle. So codimension, any hypersurface, any surface which is not, any region which is of lower dimension than that of the space-time cannot be sampled. Okay, it's a simple sampling question. So what is an example of this are things that are null, the null cone that I showed you, the light cone. The boundary of the light cone is a d-1 dimensional surface. But it doesn't appear in the causal set because of the fact that it's of lower dimensions, so it's never sampled. But we know light travels, right? I mean, as Urvashi told us, light does travel. How does it travel on a causal set, right? So one of the things we did was try to reconstruct how null GD6 come about. How do we construct null geodesics that are straight, take straight paths? And in order to do that, we used some ideas of Penrose and Kronheimer from the 60s, and the idea that there are beams that you can construct just using causality relation. Okay, and yeah, so coming to Sadiq's question, now we have to ask. So all that we were doing right now is asking a kinematic question. You've discretized it. You're telling me that this is what space-time is. Then you better tell me also where is dimension there, where is geometry, and so on. And so we have partial answers to that question. Okay. But now we want to construct a full quantum dynamics of causal sets. So it means that I should be able to look at any ensemble of causal sets and construct a quantum theory out of it. So there are different approaches to quantization, and I'll just focus on what I call the state sum models. Here, omega corresponds to the set of all possible causal sets with possibly some restrictions, and including those that look nothing like spacetime. And so if we're talking about quantum gravity, we have to look for non-classical paths, right? We have to look for things that don't look like spacetime at all, definitely do not satisfy Einstein's equations, and so on and so forth. We need to look at the full quantum theory. So we need to be looking at causal sets which are way off anything that you might think looks like a reasonable spacetime. And that's what we want to set out to do. And so let me skip this slide and just go over to the state sum models that we've constructed. And I want to say this is sort of a homegrown in-house RRI program, which if I was fancier, I would call a discrete computational geometry laboratory. But since I'm just a theorist, I am not allowed to use the word laboratory. So, and this basically tries to generate the partition function for causal sets. And here we have the omega that I have is a set of fixed n-element causal sets. And I want to construct a statistical partition function over causal sets. Okay? And that statistical function, partition function can come after analytically continuing the path integral. And what we do is we use Monte Carlo methods to generate this ensemble of causal sets, to generate a dynamics. Here's a very simple example in 2 dimensions, which I worked on, which is sort of the template based on what we've done other things. And that is a very simple Monte Carlo move that you can construct from here, which satisfies all the conditions of detailed balance and so on. One of the moves, for example, here a move would take you from this to this, okay, this kind of causal set to this one. And so what you do is then you use the Monte Carlo move to sample the entire space, or as much of it as you can, of the space of all causal sets. And in this case, we've restricted to 2-dimensional causal sets. And we use a Metropolis algorithm. It satisfies ergodicity, so on and so forth. And we get very good thermalization properties. And so we can study this system. What we find, and this is kind of interesting, is that we find that there's a phase transition. We've found out that it's actually a first-order phase transition. And it takes you from configurations that look like this to those that look like this. As you might, if you've paid attention to my earlier slides, these are good guys. These are the ones that look like space-time. These are the ones that don't. Okay? So there's a very interesting phase transition that takes place at a critical beta value, at a particular beta value, which is that parameter that I've introduced. And if I had more time, and if anyone's interested, I have a cute little movie that shows this, but I don't have it here, I have it on my Mathematica, but which basically this phase transition has been very studied in great detail, okay? So it's not something that we've just sort of looked at 2 or 3 temperatures, it's been studied with a lot of precision. And so we can map out and do a lot of analysis on this. We also constructed what's called the Hartle-Hawking wave function, which is basically telling you, it's called the wave function of the universe, if you please. But it's, yeah.
So looking at the structure when you showed the phase transition, it looks like from some kind of a disordered to an ordered state kind of things which happens in magnetism, for
Exactly.
example. So
But
is
it's
there-
not, but the interesting thing is it's not a second order phase transition.
Yeah, means.
Yeah, but
my-
exactly. So that was in fact the first thing when I looked at it, I thought that this is exactly what's happening. Later, much later, we did a very extensive finite size scaling analysis of the system. And we found that in fact you have this double Gaussian which arises, which is very characteristic of the first order phase transition.
Right.
So we showed that it's actually a first order phase transition. But it has exactly this thing, this property of being disordered to ordered. But the disordered phase here is the one that we want because that looks like space-time. But the other phase is also very interesting because it's sort of a phase in which if you look at the previous picture, sorry, now I keep doing, this one here, you see that a universe is being created, okay, and suddenly becomes very large and very connected.
So my question was,
Which to a cosmologist is particularly important. Yes,
yeah,
go
my
ahead.
question was linked. Means I know from my understanding of magnetic phase transitions, in 2D and in higher dimensions, the nature is very different. Of course, you assumed here, for the sake of simplicity, a two-dimensional
Yes.
case. So I'm sure that it's computationally much harder to go to higher.
Yeah, so we have some results, and what's interesting is that it is very similar. We
Oh.
get a very similar kind of phase transition even in higher dimensions.
So you still see an order.
Yeah, so that's my
it.
next slide. That's a good question. I'll just, yeah. So in fact here, let me just skip to that and say that, yeah, so here are cases. So the one that we looked at earlier was just a topologically trivial patch of 2D spacetime. We looked at it on a cylinder. We got the similar thing. But we also looked at it on a torus cross time, T2 cross time. And these are very, very hard, computationally very expensive calculations which had to be done, not here, were done by my collaborator on a bunch of supercomputer time that he basically took from in North America and generated this kind of phase transition, and they're very similar. So it's very interesting and ubiquitous. We have to go to 4 dimensions. That's sort of on the agenda. But just before I do, I just want to say that coming to the quantum, where of course Sadek is here and not here, truly quantum, we did look at what's called the Hartle-Hawking wave function, which is defined on the final hypersurface, final spatial boundary, and calculated what happens as the parameter, as a function of this NF, as a function of beta, which is that parameter. And you find that it forms a very nice peak on the continuum geometry, here. And there's a phase, at the phase transition, it sort of oscillates between these two, and it again forms a really nice peak on the second one, on the very ordered phase. So this again suggests that what this phase transition is and what the wave function is telling us about the early universe. I mean, this is just a 2-dimensional model, but it actually, we've run it, it's a fully dynamical, fully non-perturbative calculation. So I just want to say we also did some work on quantum fields and causal sets and so on and so forth. I will not have time to look at this. What I want to say though, that in all of the endeavors that we've had, it's been very interesting for me to make analogy with condensed matter systems and learn about condensed matter systems. Because one thing that is there about causal sets, because of the fact that there's such a long range order, all the things that we know about things like Ising models, which are typically what quantum field theory people know well, are just not relevant anymore. So one has to look at systems with long range order. And as many of you know, the phase transitions, all of the properties are very different. And in our recent study in entanglement entropy, where you expect somehow there's this holy grail of getting out area laws, we get out typically volume laws. And it's only when you restrict yourself to a certain spectrum, a truncated spectrum, that you can recover the continuum area law, or the expected area law. And again, there's sort of a very interesting set of ideas, which are the idea of entanglement probes, but basically you have, in the short range, in the low energy regime, you can only you can only get out area laws, but in the high energy regime, where you can go have probes that are like entanglement probes, they probe deep into the system and you can recover in a volume law. So these are things that are very interesting for me. And here's a very bizarre, surprising connection. Ayten Bahmat from Ben Gurion University was here, and he gave us a talk on relating Lorentzian geometry, in particular causal sets, to the airplane boarding problem. And it's something he's been working on, and there's this really amazing, surprising connection between them, which is just to illustrate the fact that even though it looks like one is going off in one particular direction, far from everything else, somebody else is there to use information and use things that you do in possibly more practical ways. So we have several things going forward, but I really hope you enjoyed the view, and some of these questions, you go back with a little bit of that with you. Thank you.
Thank you, Sumati, for a very nice talk. Is there any quick questions?
Yeah, this coming back to this aeroplane boarding.
That's the thing that I know least about.
Yeah, no, my question is not on that. So you showed this earlier thing where you look at the longest path, right?
Mm-hmm.
And if I remember from this talk, actually, he looked at this longest path, and this is distributed according to the Tracy-Widom distribution.
Mm-hmm.
So is it the same path, longest path in your earlier thing?
It is.
So that path is also distributed according to Tracy-Widom distribution?
It should be. Nobody has studied it but him. Okay? So that's the thing, that we are not worried about the fluctuations, although we know that there are very large fluctuations. Those fluctuations, I think that was when he was talking about it, it seemed suddenly like there was a connection, but those fluctuations haven't been systematically studied at all. It's absolutely and totally possible to sit down and do that and to study how those distributions work in different Lorentzian geometries. In fact, in a whole range of things that may not even be Lorentzian geometry, because even though it looks like Lorentzian geometry, this random thing, you could also go off random, and you could still define the quantity. So it's actually a very interesting question, and I think, it's an open question whether you will get that distribution.
There, if I understand correctly, so you have this set of point, and the way you draw the path is according to some rules, or is just whatever is in front of you, is it? In a light cone.
Yeah, so I don't know if I have those pictures, but let me try to draw it here. Yeah, so there's a relation. So forget about the continuum. Sorry.
Have a quick tea break and assemble at 4:15. We can.
So I'll just. So okay. So yeah, I'll just answer this one. And so suppose you have relations like this. Okay, you have a bunch of points like that, and you have any relation, right? I mean, so as long as it's a relation, you can make a chain, right? But not all of them are going to be very long. You also have a relation that goes all the way like this. So those are also relations. But now you're looking for the one that's the most kinky one you can get, right? The longest one with you grab as many events along the way as you can. That greedy path is the one that is the length of the longest chain, which corresponds to the time-like distance, proportional to the time. And people have studied that and tried to see, for example, one of the questions is, you get, if you take one single sample, I mean, because this is all like ensemble averages, right? But if you take a single sample, very often that's maybe all you have. But then you can get something really off, right? I mean, so it doesn't contain, there's no self-averaging or anything. So you get, those fluctuations are known to be there. So one ends up, if you want to get anything coherent, you have to take a very, very large ensemble and then do the averages to get the values. But this is known to have, in fact, typically they don't look straight, they look sort of a little bit, they bend around because if you don't have a large enough density. So it is a very interesting question to ask, because if we really think this is important, then those fluctuations can have potential physical consequences, right? I mean, if you think of, of course we're talking about things that are hopping around in Planck scale stuff, but still, right? There could be a secular effect, something that builds up because of fluctuations. So yeah, we've not studied them at all. So it's actually a very good open question.